Alright, so in this section we're going to be talking about polar coordinates. Most of us have probably seen these before, so these first few examples may kind of be, silly or easy for you, but they're going to lead up into building the skills that we need for the next section. So, normally, if we have some point, we call it x comma y, and we'll plot it in our xy plane. So let's take this point, for example. Right. It's got some x and y value. And given where it is, we can tell that this x and y value are positive. Well, a different way to name this point is using polar coordinates, and we use r comma theta, where r is going to be the radius, so that's the distance from the origin. Right, so this distance right here, this would be r. And then theta is going to be the degree that we're rotating from the positive x-axis. So this would be our theta. Let me draw that a little bit neater. So that's our theta. So then we call this point r comma theta. So a couple things to note is that if our angle is positive, then we're rotating counterclockwise like this. If our angle is negative, we'll rotate clockwise like this. Right? So this is for a negative angle. Just like we do on the unit circle. Now, another thing to remember is that if I take 2 pi and add it to an angle, I'm still at the same place on the unit circle as far as my angle is concerned. So, if I have some point r comma theta, and I take some integer multiple of 2 pi and add it to theta, then that's going to be the exact same point. Another thing to notice is that let's say I took this angle right here and I add pi to it. So that would look something like this. Right, so this would be theta plus pi. Now, if I had a positive r value, right, so if I took something like this, so let's say this is the same length as that blue line. So this would be theta plus pi comma r. R comma theta plus pi. We do the radius first and then the angle. Okay, now if I had a negative r, it would end up, we would basically take this orange line right here and reflect across the origin. Right, so we would end up right back over here. So it turns out that this is going to be equal to negative r theta plus pi. So it basically just says if you have a negative radius, then just travel in the opposite direction of wherever your theta is. Okay, so now let's look at example 1, and we'll plot these points and then find 2 other pairs that are equivalent to them. So we have the point 2 comma pi over 4. So that tells me that my angle is pi over 4. So this probably looks something like pi over 4. And then we have a radius of 2. So then my point would be right here, where this line right here has a length of 2. Okay, so like we mentioned, you can take 2 pi and add it to this and get the same point. So 2 comma pi over 4 plus 2 pi would be the same point. Now another way to get the same point is if we add pi to this and then multiply our radius by negative 1. So this is also going to be equal to negative 2 comma pi over 4 plus pi. Right? So here's an example where we have 3 points, 2 of them with positive radii, the other one has a negative radius, different thetas, but they all represent the exact same point in the xy plane. Okay, now let's look at part B. So we want to rotate by 3 pi over 2. So that would be to here. So that means that I'm going to be traveling along this axis right here. And then our point, we have a -2 radius. So imagine that this right here is length 2. I want to reflect across the origin, so I actually end up here. Right? So if I had +2, it would be right there. But since I have a -2, I have to go in the opposite direction. So I end up right here. So another way for me to have done this is notice that this is the same as if we just do a π/2 rotation and have a positive radius too. So then this is going to be equal to 2π/2. And then, of course, another way to do it is for us to take -2 and then add 2π to 3π/2. Okay, now let's look at part C. So for part C, I'm supposed to rotate -π/6. So that would be somewhere down here. And then we'll have radius 2. So let's say this line segment right here has length 2. Then this is where our point would be. Okay, well this is also equivalent to if I had just added 2π to the radius. Now the other point may be a little bit difficult, but the nice way to do it is with our formula, right? We could imagine where this is going to be. But remember, if we just add π to our radius, right, so this would also be equal to, we have to multiply the radius by -1, so we get -2, and then add π to our angle. So we'd have -π/6 plus π. And then I'll separate these three parts real quick. Okay, so that's just some examples of how we can plot points in the xy plane. Now I want to look at how can I convert some r, theta point into a x, y point, right? How can I go from polar to Cartesian? Some people also call Cartesian rectangular. So someone may ask you to go from rectangular to polar. That's just saying go from x, y to r, theta. So here's 3 identities here that we'll use a lot, and let's look at where these come from. This may make it easier to memorize. So let's say I have some point r, theta, and it's sitting right here. What that tells me is that this distance is r, and if I was to say make a triangle right here, then this angle right here would be theta. Okay, well then this distance right here will give me my x coordinate, and this distance right here will give me my y coordinate. And so if we take cosine of theta, that would be adjacent over hypotenuse, that'd be x over r. So if I multiply by r on both sides, we get r cosine theta equals x, which is where this identity right here comes from. And then the one for sine is very similar. Also, notice that tangent of theta is opposite over adjacent, so that's how we get this. And then if I take an inverse of both sides, I'll get theta equals tan inverse or arctan of y over x. And then finally, if I apply Pythagorean's theorem, that's how we get this last identity. Okay, so let's look at example 2. Here I have an r, theta point, and I want to find the x, y equivalent. So we have r equals 2, and theta equals 2π/3. So one of our identities is that r cosine theta is equal to x. So that means that 2 cosine 2 pi over 3 is equal to x, which means that this is going to be 2 times negative 1/2 is equal to x. So x must be equal to negative 1. Similarly, we'll have r sine theta is equal to y. So this means that 2 sine of 2 pi over 3 is equal to y, which means that 2 times square root 3 over 2 is equal to y, which means that square root 3 is going to be our y value. And so now we have that the xy equivalent of this would be negative 1 square root 3. Okay? Now I want to find, for number 3, we're given a graph. And this graph is represented by r equals 2 sine theta. And so we want to find the Cartesian equivalent. So what I'm going to do is I'm going to start with r equals 2 sine theta. And I'm going to multiply by r on both sides. So that'll give me r squared is equal to 2r sine theta. Well, we know that r squared is equal to x squared plus y squared. And we know that r sine theta is equal to y. Okay, so now I want to try to get this into something that we understand. So what I'm going to do is I'm going to subtract our 2y over to the left-hand side. And then I'm going to complete the square on y squared minus 2y. So this will turn into x squared plus y minus 1 squared. Now, notice that y minus 1 squared, this would be y squared minus 2y plus 1. So since we don't have a plus 1 over here, I need to get rid of that plus 1. So I'll do a minus 1 right here, which gives me that x squared plus y minus 1 squared is equal to 1. And so now we know exactly what this looks like. This is going to be a circle centered at 0, 1 with radius 1. Okay, now let's check out example 4. So example 4, we have to do a very similar thing. So we start by multiplying by r on both sides of the equation. So we'll get r squared equals 9r cosine theta. We'll plug in x squared plus y squared is equal to r squared. And then we'll also plug in that r cosine theta is equal to x. And so this will give me x squared plus 9x plus y squared is equal to 0. So that means that, sorry, this should be minus 9x. So this means that x minus 9 halves squared minus 81 over 4 plus y squared is equal to 0. And so then the equation that we'll get will be another circle. So we'll get x minus 9 halves squared plus y squared is equal to positive 81 over 4. So this will be a circle centered at 9 halves, 0, with a radius of 9 halves. Okay. If you've forgotten how to complete the square and this little step doesn't make sense to you, then please let me know and we can talk about it in office hours. This is something that probably a lot of us haven't used in a long time, so it's not a bad thing to ask about. Okay. Now, for example 5, we have another equation. So this is going to be r equals 5 secant theta. And at first, this looks a little bit intimidating, and looks like it could be pretty difficult. But what I'm going to do is I'm going to transform secant theta into 1 over cosine theta. So this is going to be r equals 5 over cosine theta. Now if I multiply on both sides, I'll get r cosine theta is equal to 5. Which means, if I use our identity for r cosine theta, that we have x equals 5. So this graph is actually nothing more than a vertical line at x equals 5. Okay, now let's move on to example 6. So for example 6, we're asked to find the polar coordinates of these rectangular coordinates. And furthermore, we're supposed to do it with a positive radius. Okay, so the first thing I want to do is look at part A. Alright, for part A, what I'm going to start with is that r squared is equal to x squared plus y squared. So that means that r squared is going to be equal to 9 plus 3. Because I just plugged in x equals 3 and y equals square root 3. So it tells me that r is going to be equal to plus or minus the square root of 12. Well, we know that we want a positive radius, so we're going to get rid of the minus, and so this is going to be 2 root 3. Then the next thing we know is that theta is supposed to be equal to tan inverse of y over x. So this is tan inverse of square root 3 over 3. And so then looking at the unit circle, we know that theta is going to be equal to pi over 6. So that tells me that my point is going to be 2 root 3 comma pi over 6. And just to make sure that this makes sense, I'm going to go ahead and graph it. So I know that 3 root 3 would end up somewhere in here. And this does look to me like this may have a radius of 2 root 3 and an angle of pi over 6. Okay, so it's believable that we got the right answer there. Now let's look at part B. So again, I'll start by finding r. So I'll have that r squared is going to be equal to x squared, which is 9, plus y squared, which is 16. So this is going to be 25. So it tells me that r must be equal to positive 5. Remember, we get that by taking the square root of 25 and then eliminating the negative, since we have this requirement right here. Okay, so theta is going to be tan inverse of 4/3. And we don't know what tan inverse of 4/3 is. We don't have anything nice like that on the unit circle, so we're just going to leave our point as 5, comma, tan inverse 4/3. Okay, and we'll go ahead and plot this. 1, 2, 3. 1, 2, 3, 4. So it's believable to me that this has a radius of 5, and that this theta right here is going to be tan inverse of 4/3, even though we're not sure what that is. So now, in this next problem, you'll see why I've been graphing these. So, this next problem I have r squared is equal to 4 plus 4. That's going to be 8, which tells me that r is equal to, we're going to have to take the positive one, so this will be positive 2 root 2. Now we'll look at finding theta. So theta is going to be tan inverse of, let's see, this should be y over x, so 2 over negative 2. So that's negative 1, which tells me that theta should be equal to negative pi over 4. Now let's graph this real quick. So negative 2, comma 2, that would be right here. But notice this angle and this angle, neither one of these are negative pi over 4, right? So what that tells me is that I need to adjust our theta. If we did theta equals negative pi over 4, we would end up and have a positive radius, we would end up down here. So then what I need to do if I want to keep my radius positive is that I need to add pi to theta. So I'm just going to mark this as wrong. However, if I add pi to it, then everything will work out. So we get that our point is going to be 2 root 2 negative pi over 4 plus pi. Okay, now let's look at example 7. For example 7, we're asked to find the polar equation for the curve described by the given Cartesian equation. So here I know that x is equal to r cosine theta, so I'll write r cosine theta is equal to 6, which means that r is equal to 6 over cosine theta, which is 6 times secant theta. Next, we'll take a look at part B. So we have y plus x is equal to 1. Well, it tells me r sine theta plus r cosine theta is equal to 1. I can factor out an r to give me r times sine theta plus cosine theta is equal to 1. So then r will be equal to 1 over sine theta plus cosine theta. Finally, we'll take a look at part C. So for part C, plugging in x equals r cosine theta, that would give me r squared cosine squared theta is equal to 4y. Well, y is equal to r sine theta, so this is going to be 4r sine theta. And so what I'll do here is I'm just going to leave this because we have to look at a lot of things that are going to be going on here. One, if I decide to divide by r on both sides, then I could possibly be dividing by 0, right? Notice that a solution to this equation would be we plug in 0 for x and 0 for y. And so one of our points should be 0, 0. Well, that would have a radius of 0. And so if I divide by r on both sides, I'm dividing by 0, and that's going to cause issues for us. So what I'm going to do is leave our equation like this because there's no point in simplifying further. Really, if you had written something like this for these two, these would have also been acceptable answers. I just wanted to show ways that maybe you could see these simplified on an exam. So for part A, we have r equals 4. So this is just going to be a collection of points that are 4 units from the origin. So what this is this is a circle of radius 4. So then the region being described right here is just this curve of the circle. Now let's look at part B. So part B is a little bit more interesting because now we have an inequality. So let's look at the smaller one. So r has to be greater than or equal to 2. So that's going to be all points that lie outside of the circle centered at the origin with radius 2. Okay, so that would be this. Now, since it's greater than or equal to, I'm not going to dash this line because we're including this curve. But then we want those points to also be less than 4 units from the origin. So now what I'll do is I'll take a circle of radius 4 and we'll use a dashed line to emphasize the fact that we can't include points that are on this curve. Alright. Now for part C is a little bit more interesting because now we're not dealing with r anymore. Instead, we're dealing with theta. So here's what I want to look at. We know that theta can be between 0 and pi over 3. Okay. So my first, I guess, intuition here is, okay, so we include theta equals 0. So that would be this right here. This would be a line that has an angle of 0 from the x-axis. And then we go to pi over 3. So that's somewhere up here. Right? And so I include this line as well. So now imagine that r can be anything it wants to be. So that means I can go anywhere I want along these lines. I can also go in between them because our inequality states that theta is going to be in between these. So I could choose something like pi over 4. And I'd also be including all points on that line. So that means that I'm going to be including everything in this area. Now what if, so let me take this again. Now what if we had theta was equal to pi over 3, but our radius was negative? Well, that would mean that I would be traveling in this direction. Right, so this is when r is negative. So I have to include everything on this line. Well, what if theta was equal to 0, but r was negative? So that means I'd have to travel along this line right here. Right, so this is again when r is less than 0. And so that means I have to include everything in between these two lines, so I'm also going to include everything in this region. Right? And so the way that we get this is we have to consider points where r is less than 0. Okay? And then similarly over here, this is when r is greater than 0. And then this beautiful point right here at the origin is when r is equal to 0. Okay. Now let's consider part D. So I'm going to start with the part where it says r has to be greater than or equal to 0, but less than or equal to 2. Alright, so that means I'm in between a circle of radius 0. Well, that's just the point at the origin. I'm in between that and a circle of radius 2. Right. So then this tells me that I'm going to be including everything inside the circle. But the next criteria says that theta has to be in between pi over 2 and pi. So that means that we have to be in between here and here. So then the area that we're actually looking at is in here. Now notice I don't have to do what we did last time of worrying about any sort of reflection or r being negative, because we have that r is strictly between 0 and 2. Okay, now let's look at example 9. So now we're going to start giving ourselves some formulas that will be highly useful for us to automatically notice graphs in the future. So we have r equals 3 cosine theta right here. Well, if if theta is equal to 0, then we get 3 times cosine of 0. Well, that's 3. If theta is equal to pi over 2, then we would get the point at 0. If theta was equal to pi, right, so this would be pi over here, then r would be negative 3. So that means that we would end up back over at this point again. So what's happening here, if we consider the fact that we're going to be traveling at all sorts of angles in here, And then once we get to the angles over here, we get negative radii, so we actually end up hitting these. What's happening here is that we go 3 units along, sorry, these shouldn't be dashed. We're going 3 units along these black lines every time. And what we end up getting is this circle. Okay, and so the thing to notice here is that r equals a times cosine of theta, where a is some real number. This is a circle along the x-axis with radius equal to a. Similarly, r equals a sine theta. It's going to be a circle along the y-axis with radius equal to a. This is going to be very important. Being able to identify these immediately is crucial. The other crucial thing to notice is that, right, remember how I said whenever our theta's in this area, then we end up traveling along these lines down here? And so we'll end up hitting those points. That means that we generate the full circle when theta goes from 0 to pi. Okay? We won't use that fact this section, but it's going to be extremely important in the next section. Okay? So now let's look at example 10. Example 10 asks us for the graph of the polar equation r equals negative 2 sine theta. So I know this is going to be a circle of radius 2 along the y-axis. I just need to figure out, okay, does it look like this or does it look like this? So the way for me to figure that out, if I just plug in some theta where I'm not going to get r equals 0, so I'm going to plug in theta equals pi over 2. Then I would get r equals negative 2 times 1, which gives me negative 2. Notice pi over 2 is up here, so I would travel in the opposite direction since I have a negative radius. So the circle we want is the one with the point down here. Okay, so we can see from this, if we have a positive a, then our circle will be above the x-axis. If we have a negative a, it'll be below the x-axis. Similarly, if I have a positive a for cosine, or a cosine theta, then our circle will be to the right of the y-axis. If I have a negative a value, then it will be to the left of the y-axis. Okay, now for example 11, this one's a little bit different. So for example 11, what I'm going to do here is I'm going to plot out some points. So when I have theta is equal to 0, then this will be 1 plus cosine theta, so that'll be r equals 2. So here's theta equals 0, and r is going to be equal to 2, so I get this point right here. Now when I have theta equals pi over 2, we'll get r equals 1. So that'll be right here. When theta is equal to pi, we'll get 1 plus negative 1 is 0, so that'll be right here. And when I have, sorry, that was pi. When I have theta equals 3 pi over 2, I'll get 1 plus 0 is 1, so I end up right here. And so what this graph looks like, actually, is a heart. It's a pretty lovely graph. And this type of graph is called a cardioid. Now notice I had to go to pi over 2 to get this point. I had to go to pi to get this point. I had to go to 3 pi over 2 to get this point. And I'd have to go back. I'd have to go all the way to theta equals 2 pi to come back to our starting point. So what this means is that our cardioid is generated when theta goes from 0 to 2 pi. Again, extremely important fact for the next section. Can't state it enough times. Okay, so here's some tricks. Whenever you have, let's see, what color do we want to use? Let's use plum. Whenever we have r equals a plus a cosine theta, that's going to be a cardioid that looks like this. Oh boy. Alright, also I forgot to mention, this is the section where you have to really imagine that you have a professor that can draw. This is probably like the worst part of the semester to have me because I cannot draw. So stuff like this, that's supposed to be a heart, right? It's supposed to be a cardioid. It may not look like that. Similarly, if I have a minus a cosine theta, a minus a cosine theta, then it would look something like, oh boy, how do we draw this? Yikes. Something like that, right? So instead, it's kind of like you can imagine we would just flip this. So I'd get something that looks like that. That's what I'm trying to draw for the a minus a cosine theta. Now let's look at what if we have r equals a plus a sine theta. Well, in that case, we would get a cardioid that looks like this. And then if I have r equals a minus a sine theta, sorry, yeah, this is good. A minus a sine theta, then it would look like this. Okay. The biggest thing to remember is that a plus or minus a cosine theta is going to be horizontal, and then a plus or minus a sine theta is going to be vertical. After that, you can kind of figure it out from there. So I'll show you what I mean by on this one. So the quick way to do this is to notice that our a value will give me this point, right? If we know that this is going to be a vertical one, it gives me this, it'll give me this, and this, right? This would be 2a. Okay, and so my graph ends up looking something like this. Now, like I said, if you just remember that it's vertical, we can figure it out from there. The way we do that, if I start off with theta equals 0, I would get 1 minus 0, so that gives me this point right here. And then theta equals pi over 2. That would give me 1 minus 1, so that would give me this point right here. With theta equals pi, that would give me 1 minus 0, so we get this point right here. And then finally, with theta equals 3 pi over 2, we would have 1 minus negative 1, so that would give me 2, which gives me this point right here. Okay, and so then from there we can figure out which direction our cardioid is facing. Again, we'll need to go from 0 to 2 pi to generate this entire graph. Now let's look at the next one. So here we're going to be dealing with roses. So if we have sine of k times x, if we have r equals sine of k times x, or, oh, this is a typo, I'm sorry. This right here, this should be sine of k times theta. And this should be cosine of k times theta. This is not a KO, this is k times theta. Okay. So, here's what I'm saying here. If k is odd, then the graph will have k petals. If k is even, then the graph will have 2k petals. So let's look at this. Let's say we have something that looks like r equals cosine 5 theta. Then what that tells me is that this is going to have 5 petals. So it looks something like this. And we also know that every time in these graphs, these petals are supposed to be evenly spaced apart. However, my graphs are not going to look like that. There's 1, 2, 3, 4, 5. So that is what this graph would look like. Now, whenever your k value is odd, so for an odd k value, theta must go from 0 to pi in order to get all of the petals, right? In order to generate the full graph. Now let's say we have something that looks like r equals cosine 4 theta. So for this, since k is even, that tells me that I'm going to have 2 times 4 petals. So I'll have 8 petals. And so that will look something like this. Again, they're all supposed to be evenly spaced apart. I also know that for cosine k theta, my first petal always starts on the x-axis. What I mean by that is that here's my first petal starting on the x-axis, here's my first petal starting on the x-axis. So that's a pattern for your cosine of k theta. Now let's look at, so let me make sure I got that right. 2, 4, 6, 8. Yep, I got 8. They're just really weirdly shaped. They're also all supposed to be the same size, right? So if we kind of think of like the area in here, this should be symmetric about the x-axis. It's not because my drawing is awful, but it's supposed to be. Okay. It also means that, like, if I was trying to find the area inside of all these loops, I could just find, so like for this one, I could just find this one area in here and then multiply it by 5 in order to get all of them, since all of these are the same sized petals. Okay. Now I want to look at what happens when we have an even k. So for even k, theta must go from 0 to 2 pi in order to get all of the petals. Okay, so that shows you what cosine of k theta looks like. Now let's look at sine of k theta. So for this one, let's assume we have r equals sine of 3 theta. So I have an odd k value, which tells me I should have 3 petals. And so this will look like this. And now let's look at something that's going to look really bad, which is r equals sine of 6 theta. So that tells me that I should have 12 petals. And since this is sine of k theta, I know that I'm going to have 4 quadrants. So I'll have 3 petals in each quadrant. I'm going to start with drawing the middle one. Now I'll try to fill in the others. Again, forewarning, you may want to look this up on Desmos if you're like, what in the heck is this? It's supposed to be a flower with 12 petals. It is not turning out like that. They're also not supposed to overlap, right? But that's just kind of how my drawing came out. Okay, so for example 13, we're asked to sketch the graph of r equals cosine 2 theta. Well, I know that k is even, so I should have 4 petals, and cosine starts on the x-axis. So notice here, if I plug in theta equals 0, this would be r equals cosine of 0, so this should go to 1, so that's how I know what this distance is. Right, now if I had like r equals 2 cosine 2 theta, then all I'm doing is changing the length of these petals. Or even like r equals 3 of cosine 3 theta. So that means that instead this petal would have looked like this. And then I'd have to similarly adjust the size of all the other ones. Okay, and then for our last example, example 14, we'll be looking at the graph of r equals sine of 3 theta. So we have an odd k value here that tells me that I'm going to have 3 petals. To figure out where these petals are is a little bit difficult at first if I'm graphing this on a graph. So notice if I plug in theta equals 0, then r equals 0. So that just gives me this point right here. Another nice one might be theta equals pi over 2, but it's actually going to skip a lot of points. So what I'm going to do is I'm going to start looking at each theta on the unit circle. So the next one would be, right, if we imagine our unit circle. Right, this would be theta equals pi over 6. Theta equals pi over 4, and this would be theta equals pi over 3. So if I plug in pi over 6, then we'd have 3 times pi over 6, so that gives me 3 pi over 6, which is pi over 2. So I would need to go 1 unit along this black line. Okay. Now, if I have pi over 4, that would give me 3 pi over 4. Sine of 3 pi over 4, right? So we need to remember, where is 3 pi over 4? Well, on the unit circle, that's the one that's over here. And so that's going to be square root 2 over 2 radius, right? So that'd have to be somewhere in here. So what this tells me is that my petal is going to look something like this. And then I'll get another one at 5 pi over 6. So this one's at theta equals 5 pi over 6. And then finally, I'll get another one down here. Okay, so this should be a good introduction into how do we plot stuff in polar coordinates and how do polar coordinates actually work. Next section, we'll actually start doing some calculus with polar coordinates.